They've been called controlled collisions. Approaching at speeds of more than 140 miles per hour and sync rates of over 20 feet per second, naval combat aircraft must repeatedly slam on the carrier decks and be hauled within seconds to an abrupt stop. They have to be rugged to withstand this type of punishment. The structural strength translates into added weight, which cuts down on performance, range, and load-carrying capability. How rugged is rugged enough? But what about carrier launches? A catapult, mechanical slingshot, can hurl an airplane from 0 to 140 miles per hour within 2.5 seconds. How do you ensure smooth, fully controllable flight as the airplane quickly transitions from wheels and flaps down to a clean configuration, and the aerodynamic forces change in volume and intensity at an incredible rate? Though unique to naval operations, these are only a couple of the myriad of questions that aircraft designers must consider as they attempt to hone their craft into something better, more effective than anything which has preceded it. An incredibly complex array of factors come into play as they attempt to overcome problems impacting airspeed, maneuverability, range, weapons delivery, systems integration, maintainability, and, the bottom line, cost and schedule. All of these and a host of other questions must be answered to the designer's satisfaction before he can answer that most important question of all. Will his design meet the requirements? Will it get the job done? This man answered those questions about as well as anyone in his profession ever has. One of the most prolific and innovative designers of all time, Ed Heinemann, was regarded as the master of fundamental simplicity in aircraft design, and the family of airplanes he built established him as one of the true giants in the world of aviation. Not bad for a man who quit high school in 1925 to pursue a career as a draftsman. Within a year, he found himself working at the Douglas Aircraft Company in Los Angeles. Donald W. Douglas founded his aircraft company in Santa Monica in 1920. In 1932, he acquired the Moreland factory, expanding his operations. Around this time, Douglas negotiated a partnership with John K. Northrop, who would later become a legendary figure in aviation. Northrop began producing aircraft designs at the former Moreland factory, now renamed the Northrop Division of the Douglas Aircraft Company. The plant started with just 15 employees, including the young designer Edward H. Heinemann. Heinemann had previously worked as a draftsman for Moreland Aircraft and Lockheed Aircraft Company. Under Northrop's mentorship, he honed his skills in aircraft design, paving the way for his own distinguished career in aviation. During this period, Northrop designed the Alpha, a single-engined passenger and mail-carrying aircraft of all-metal construction, with open cockpit behind an enclosed cabin, and the Beta, a small two-seat all-metal sports aircraft. However, in September 1931, the United Aircraft and Transport Corporation decided to consolidate its two subsidiaries, the Northrop Aircraft Corporation and Stearman Aircraft, into a single corporate entity and to center all the operations of the enlarged company in Wichita, Kansas. The initial objective of the new company was to design and build two series of aircraft, which, continuing the tradition of naming its aircraft after Greek letters, became the Gammas and the Deltas. Whereas the Deltas were conceived initially as passenger-carrying aircraft, the Gammas were designed as special-purpose and mail-carrying aircraft. The Gamma design also played a significant yet less glamorous role as 49 aircraft were completed by Northrop, and the type was developed into the A-17 series of attack aircraft for the Army Air Corps. Although it did not achieve success, the next type of airplane designed by the Douglas subsidiary, the XF-T-1 experimental naval fighter, marked the beginning of the association between the Northrop Corporation and the U.S. Armed Forces, particularly the U.S. Navy, and for the first time gave Ed Heinemann the job of project engineer and responsibility for detailed design. At 235 miles per hour, the XF-T-1 easily proved to be the fastest aircraft in the competition, but marginal handling qualities cost Northrop the contract. The XF-T-1 served as the basis for the Model 3A proposed Army fighter. Ed Heinemann actually completed the detailed design and construction of this airplane all within 30 days. Featuring retractable landing gear, the 3A also boasted exceptional performance and impressive 279 miles per hour, but it too suffered from marginal stability. Upon receiving the Navy's invitation to bid on June 1, 1934, the Northrop Corporation selected Ed Heinemann to serve as project engineer for the program. Under the general supervision of Jack Northrop, Heinemann prepared the initial general arrangement drawings and design layouts together with the details of the proposal for the Navy's evaluation, in competition with the proposals submitted by the other 5 contractors. The Northrop proposal was favorably received by the Bureau of Aeronautics, and even though 2 of its competitors had substantially better calculated performance, one prototype of the Northrop XBT-1 was ordered on December 12, 1934. The initial design work began in 1935. The aircraft was powered by a 700-horsepower Pratt & Whitney XR1535-66, a double-row air-cooled radial engine. It featured hydraulically actuated perforated split flaps, which also functioned as dive brakes, and a main landing gear that retracted backward into streamlined fairings beneath the wings. On 28 November 1936, a change to Contract 50517 was approved by the U.S. Navy. Under its terms, Northrop was authorized to proceed with the modification of a BT-1 to incorporate a fully retractable main undercarriage folding laterally into flush-wing wells. So modified, the aircraft was redesignated XBT-2. Completed and test flown on 22 April 1938, the XBT-2 was initially powered by the same 825-horsepower Pratt & Whitney R1535-94 as the production BT-1s. However, following an unfortunate wheels-up landing accident, Douglas decided, under authority of a new contract change dated June 21, 1938, to install the 1,000-horsepower Wright R1820-G133 with a 3-blade constant-speed propeller. To maintain aileron control after a stall, fixed leading-edge slots were also investigated and adopted. The results of these numerous modifications were rewarding, and the XBT-2 was now representative of the production model which had been ordered on the 8th of April, 1939. The 36 aircraft covered by the initial contract, number 65969, were designated SBD-1, reflecting both the change in mission to scout bombing and the change in manufacturer's name, since in late 1937, the Northrop Corporation had given place to the El Segundo plant of the Douglas Aircraft Company. The Douglas SBD Dauntless was a carrier-based dive bomber that played a crucial role in the Pacific theater of World War II. Developed in the late 1930s, it featured rugged construction, excellent handling, and a distinctive perforated dive brake system that allowed for precise, steep-angle bombing. The Douglas SBD Dauntless was involved in the World War II Pacific theater from day one. In service for roughly 6 months prior to Pearl Harbor, the Dauntless was the Navy's primary dive bomber in the early years of the war and has been credited with sinking one of the first enemy ships of World War II. The mighty Japanese fleet had expanded its conquests over the entire Western Pacific. Numerically far superior to the now mangled American fleet, it appeared to be almost invincible. The Japanese High Command planned for a decisive battle in the late spring of 1942, which would force the U.S. to sue for peace. Their plan? To attack the island of Midway and thereby draw the remnants of the U.S. Pacific Fleet into a decisive engagement, which would result in its destruction. In early June, a massive armada, including 4 Japanese carriers, steamed toward Midway. Unbeknownst to the Japanese, however, the Navy had deciphered their codes, and though vastly outnumbered in terms of firepower, had 3 carriers lying in wait, hoping to spring a trap. SBDs used a dive angle of about 70 degrees, virtually straight down, which provided 2 great advantages. First, with an angle that steep, it was difficult for Japanese gunners to score hits. Guns on the carriers had to be elevated to high angles, making tracking and leading much more difficult. Barrage fire forced an aircraft to fly through the anti-aircraft fire, but because of the high dive angle, they quickly traversed the area. Second, high dive angles significantly enhanced bombing accuracy. Shallow glide bombing often resulted in short hits and made the attacking aircraft more vulnerable. Hurling yourself at the ground, as dive bomber pilots often described the act, required a lot of training. This steep diving technique allowed pilots to maintain visual contact with their targets longer, making precise adjustments before releasing their bombs. Ed Heinemann was later to observe that the Dauntless turned out to be the right plane at the right place for the right war. On a violent June day, it certainly was. The rugged SBDs and their courageous crews were responsible for sinking all 4 Japanese carriers in a battle which had indeed become the turning point of the Pacific War. The destruction of the Akagi, Kaga, Soryu, and later the Hiryu shattered Japan's striking power and forced the Imperial Navy onto the defensive for the rest of the conflict. Even if Ed Heinemann and the Dauntless had never achieved anything else, they would have established their importance in history just on the basis of this single battle. But the SBD, which is generally regarded as the finest dive bomber ever built, went on to be one of only 2 naval combat aircraft that saw action throughout the entire war. While even before the SBD had triumphed at Midway, there were other Heinemann-conceived airplanes already in action. Back in 1936, he conceived the Model 7A as a high-performance, land-based light bomber capable of speeds in excess of 250 miles per hour. As this design was under development, however, the Army Air Corps changed its tactical requirements, asking for greater range and doubling the bomb load to 1,200 pounds. Thus, the 7A was transformed into the Model 7B prototype by late 1938. By that time, the storm clouds of war were gathering over Europe, and the French ordered 100, and then 170 more, went into service as the DB-7 in 1939. These aircraft entered combat against the Germans in May of 1940, and after the fall of France, were transferred to the Royal Air Force, which flew them in great numbers throughout the rest of the war. They came into service with the U.S. Army Air Forces as the A-20 Havoc in late 1940. Capable of speeds well in excess of 300 miles per hour and serving principally as low-level attack bombers and potent gun platforms, Havocs were employed by 9 different air forces in every theater of operations throughout the war. To the crews of all nationalities who flew them into combat, the Havoc's exceptional handling qualities and inherent ruggedness in the hostile low-level environment were a godsend. Among them, it earned admiring respect because of its ability to put its weapons on target, take an incredible amount of punishment, and still bring its crews home. It was this ability to get the job done, a characteristic of all Ed Heinemann airplanes, that led to a production run of nearly 7,400 airplanes, more than any other aircraft produced by Douglas during World War II. Much of the success of this and succeeding programs was due in no small part to Heinemann's ability to put a development team together and use it effectively. He believed in delegating authority and responsibility. Like all great designers, he could be stubborn, even rigid, when it came to demanding very thorough and exacting engineering standards, and he always had the final say on any important issue. But the basis for his approach to any problem was to build consensus among all involved so they'd work together effectively toward a common goal. He often remarked that perhaps the most important key to his success was his ability to select and hire good people, and then make the best use of each of their individual talents. Shortly after becoming chief engineer, he brought Leo Devlin on board to help with the Havoc program. Devlin would remain as his second in command for the next 2 decades. Hank Holden and Al Leonhardt would come on board shortly thereafter, and all of them would stay. By the early 50s, in fact, the group came to be known as the Four Horsemen of El Segundo. Even as the earliest model A-20s were coming off the production line, the Army Air Forces expressed interest in a light bomber featuring heavier armament, more strength, more speed, and better performance. While many within the company argued that the A-20 could be upgraded, Heinemann held out for an entirely new airplane, and within 2 weeks delivered a concept for a heavier, though only slightly larger airplane with increased speed, range, and performance, and able to carry more than double the payload. To improve stability and control for combat air crews flying on the deck, he incorporated a new laminar flow wing into the design of an aircraft that would become famous as the A-26 Invader. A-26s didn't enter combat in numbers until late 1944, but performing both low-level attack and medium-altitude precision bombing missions, they quickly earned a reputation as the Air Force's most effective twin-engine bombers. Indeed, the Air Force was so impressed that the Invader was chosen as the standard light bomber for the post-war force. A decision which proved wise when in June of 1950, the North Koreans spilled over the 38th parallel. In Korea, more than a decade after it was first conceived, the recently redesignated B-26 flew both the first and last combat missions of the war, and in between, it proved to be an awesomely effective platform as it performed interdiction missions against enemy troop and supply movements, both during the day and at night. Remarkably, in an age when jets were taking over the skies, some 400 of these vintage prop airplanes flew more than 70,000 combat missions. To ruggedness and effectiveness, Ed Heinemann would be able to add the word durable to the list of adjectives describing his designs. But the Invader wasn't done yet. A small number were modified to perform counterinsurgency missions in the Vietnam conflict of the 60s, and thus this remarkable craft could lay claim to being the only American airplane ever to see combat service in 3 different wars. As the Invaders were still rolling off the production line back in 1944, Heinemann was facing a dilemma: the strong possibility that Douglas El Segundo would soon be without a major production contract. He'd designed a follow-on to the Dauntless, the gull-wing 2-seat XSB-2D, but built according to specs laid down before the war and loaded down with systems required by the Navy, he was already obsolete by the time it first flew in early 1943. At the Navy's request, he'd modified the design into the BTD-1, a single-seat torpedo bomber which first flew in March of 1944. He was well aware, however, that this airplane would be outclassed by competing aircraft designed from the outset as single-seaters. And thus, at a meeting with Navy officials in Washington in June 1944, he made a bold proposal to cancel the BTD and allow him to use the remaining funds to design an entirely new airplane. All he'd need to complete the initial concept design would be about 30 days. The Navy was intrigued, but gave him less than 20 hours to come up with concept drawings and weight and performance estimates. That night, Heinemann, Leo Devlin, and aerodynamicist Gene Root worked feverishly in a hotel room to complete the task. And by 3 a.m., Heinemann had sketched out the concept drawings for an airplane that epitomized his commitment to the precepts of simplicity and practicality. He got the go-ahead, but had only 9 months, 6 months less than his competitors, to put an airplane on the ramp. He'd promised that the BT-2D would offer significantly improved range and vastly improved load-carrying capability while coming in at a gross weight of no more than 16,500 pounds. Weight is the arch nemesis of any designer, and to achieve his goal, he established a target figure that was underweight by 750 pounds and some very rigid design policies, such as a rule that no component could be overweight unless an equivalent amount was saved elsewhere. And to get to first flight on time, a rule that no design or fabrication decision would be allowed to remain unresolved overnight. A trip to the combat areas of the Pacific, where he interviewed air crews and maintenance personnel, reconfirmed his commitment to simplicity of design in order to eliminate weight, and unnecessary complexity, as well as to reduce maintenance time by 50%. With this in mind, he convinced the Navy to let him eliminate an internal bomb bay, saving 200 pounds and permitting the airplane to carry a greater variety of external stores. The SBD had been configured with 6 fuel tanks. He saved another 270 pounds by consolidating this complex system into a single tank. And by the time the prototype XBT-2D made its first flight in March of 1945, he'd sliced a full 1,000 pounds off the guaranteed gross weight, thereby automatically increasing its load-carrying capability by an almost equivalent amount. Capable of carrying a bomb load nearly 5 times that of the SBD and delivering it with far greater precision. The XBT-2D, originally called the Dauntless II, proved itself to be everything the Navy had asked for in a dive bomber torpedo attack airplane. But the recently redesigned A2D Skyraider series of aircraft proved to be much more in the hostile skies over Korea. The Skyraider was produced too late for use in World War II, but became the backbone of United States Navy aircraft carrier and United States Marine Corps strike aircraft sorties in the Korean War, with the first ADs going into action from Valley Forge with VA-55 on July 3, 1950. The low-wing monoplane design started with a Wright R3350 duplex Cyclone radial engine, which was later upgraded several times. The aircraft had distinctive large straight wings with 7 hardpoints apiece. The Skyraider had excellent maneuverability at low speed and carried a large amount of ordnance over a considerable combat radius. It had a long loiter time for its size compared to much heavier subsonic or supersonic jets. During the Korean War, AD Skyraiders were flown by only the U.S. Navy and U.S. Marine Corps and were normally painted in dark navy blue. It was called the Blue Plane by enemy troops. Marine Corps Skyraiders suffered heavy losses when used in low-level close support missions. Most of those were due to the tremendous power of the AD. ADs that were waved off during carrier recovery operations were prone to performing a fatal torque roll into the sea or the deck of the aircraft carrier if the pilot mistakenly gave the AD too much throttle. The torque of the engine was so great that it would cause the aircraft to rotate about the propeller and slam into the sea or the carrier. The U.S. Navy adopted the A-1 in Vietnam because its rode-ably low speed, long endurance, improved ruggedness made it ideal for low-level helicopter escort and ground fire suppression duties. The Navy AD series was initially painted in ANA 623 glossy sea blue, but during the 1950s, following the Korean War, the color scheme was changed to light gull gray and white. Initially using the gray and white Navy scheme, by 1967 the USAF began to paint its Skyraiders in a camouflaged pattern, using 2 shades of green and 1 of tan. The U.S. Navy adopted the A-1 in Vietnam because its maneuverability at low speed, long endurance, improved ruggedness made it ideal for low-level helicopter escort and ground fire suppression duties. It probably gained its greatest fame flying extremely hazardous rescue missions under the call sign Sandy. The Sandys, flying in conjunction with Jolly Green Giant rescue choppers, took on the job of locating downed air crews. Rescue helicopters were too vulnerable to operate alone, making an escort necessary. The preferred choice was a flight of A-1 Sandys. Armed with guns, bombs, and rockets, the Sandys kept enemy ground forces at bay while also providing additional support. Their mission included escorting the helicopters, conducting a general search for the downed air crew, communicating with survivors via radio, and pinpointing their exact location. Before the helicopters moved in, the A-1s also suppressed any hostile forces in the area. Even as the first Skyraiders were coming off the production line back in 1945, their piston engines had been overtaken by new turbojet technology, which promised the performance to propel aircraft through the transonic and perhaps even into the supersonic region. The problem facing the aeronautical community was that no one knew anything about the transonic flight regime. Wind tunnels had proven useless. Thus, in conjunction with the National Advisory Committee for Aeronautics, or NACA, the military services decided to build research airplanes to gather the information. The Air Force opted for a radical rocket-powered design, the Bell X-1, while the Navy took a more conservative approach and awarded Douglas a contract to build 6 jet-propelled airplanes to be designated D-558. As design of these aircraft proceeded, Ed Heinemann and his team became aware of German wartime research into swept wings and convinced of the value of employing rocket power to probe the supersonic region. Thus, 3 of the airplanes were designated D-558-2, and a parallel design effort on these aircraft got underway as work on the D-558-1 proceeded. Heinemann and his design team were treading on new ground. They'd never worked on a jet design before. Thus, once again, he opted for simplicity, wrapping a small, cigar-shaped fuselage around the 5,000-pound thrust power plant and employing conventional airfoils and flight control surfaces. After it was rolled out of the El Segundo plant in February of 1947, the Sky Streak, as it was called, was trucked up to Muroc Air Force Base on California's high desert, where in April, Douglas test pilot Gene May completed its maiden flight. The Sky Streak wasn't designed to set records. As he recalled later, Ed Heinemann never viewed it as anything more than a methodical way to obtain technical data. But that August, Navy test pilot Commander Turner Caldwell flew it to an official world speed record of 640 miles per hour, only to be surpassed less than a week later by Marine test pilot Major Marion Carl, who exceeded 650 miles per hour. This impressive performance was overshadowed less than 2 months later, when on October 14, 1947, the Air Force's Captain Charles E. Chuck Yeager flew the more radical rocket-powered X-1 through the sound barrier. But the Sky Streak went on to more than prove its worth, flying as Heinemann had intended, an extensive research program gathering invaluable data on transonic loads and flying qualities. In the meantime, the much more exotic D-558-2 commenced its flight test program at Muroc in February 1948. Initially configured with only a small 3,000-pound thrust jet engine, the airplane was woefully underpowered and unable to exceed 600 miles per hour. While performance with a combined jet and rocket boost system improved to a top speed of 720 miles per hour, the airplane was still far from realizing the potential which had been designed into it. That potential wouldn't begin to be unleashed until the concept of fuel-consuming ground takeoffs and the heavy hybrid propulsion system were discarded in favor of air-launching a fully rocket-powered airplane. Only in this configuration did the D-558-2 truly become a sky rocket. Aerodynamicists predicted that it might be capable of speeds as high as Mach 1.6, but it would far surpass their expectations. During 1951, Douglas test pilot Bill Bridgman launched away from a modified B-29 7 times and completed a remarkable series of flights, including a record top speed of Mach 1.88 and an unofficial world altitude record of more than 79,000 feet. Then, in August 1953, Marine test pilot Marion Carl extended the skyrocket's altitude record to more than 83,000 feet. Finally, on November 20th of that year, NACA test pilot Scott Crossfield sought to coax maximum performance out of the airplane and become the first man to fly Mach 2. Following launch, he ignited the engine and pulled into a climb. Flying a very carefully defined profile with great precision, he climbed to a peak altitude of 72,000 feet and then nosed over into a dive. And at 62,000 feet, he became the first man to fly at twice the speed of sound, attaining a top speed of 1,291 miles per hour, or Mach 2.005. The flight was a milestone event in the history of aviation and a signal achievement both for the skyrocket's pilot and for the modest, self-educated engineer who had led the team which designed it. In late 1945, the U.S. Navy was searching for a new carrier-based fighter that was jet-powered and could fly in all weather. The two-seated twin-engine fighter was to be equipped with a radar and with specifications for a top speed of 500 miles per hour, an operating altitude of 40,000 feet, and able to detect an enemy 125 miles away. Led by designer Ed Heinemann, Douglas produced the designs that the U.S. Navy thought suited best and was offered a contract for 3 prototypes under the designation XF3D1 with the nickname Skyknight on March 3, 1946. The XF3D1 prototype made its first flight on March 23, 1946-1948. However, despite its status, the F3D1 did not meet all standards for aircraft carrier operations, mainly due to underpowered engines. As such, priority shifted towards the F3D-2 variant, and only 28 F3D-1 planes were produced. While the F3D-1 stayed stateside to train pilots and radar operators, the F3D-2 was sent to the Korean War in the spring of 1952. Only one F3D Skyknight was shot down during the duration of this war. After the Korean War, the F3D Skyknights became used as trainers or testing beds for the then-new air-to-air missiles, AAM, such as the AIM-7 Sparrow missiles. In 1962, the F3Ds were renamed the F-10 Skyknights, with the F3D1 and F3D2 being redesignated as F-10A and F-10B, respectively. These would later be used in Vietnam, making the Skyknights the only jet fighter to have flown in the Korean and Vietnam War. The Douglas A2D Sky Shark grew out of a post-World War II United States Navy need for a prop-driven carrier-based strike aircraft offering good operational range with comparable performance to early-generation turbojet-powered Navy types. The A2D was essentially an offshoot of Douglas's classic A2D Skyraider of Vietnam War fame, which was already enjoying success in service since its introduction in 1946. Despite this, the A2D was nearly an all-new, largely separate development due to the changes required to meet the new USN need. Despite its promising design, the A2D was limited to just 12 aircraft as issues with the intended Allison engine fit were never fully resolved while progress on turbojet technology was made. The Douglas A2D Sky Shark was powered by an experimental twin-turbine engine, producing a whopping 5,000 horsepower and driving a pair of huge 3-bladed counter-rotating propellers. The Sky Shark demonstrated some very impressive performance. Takeoff in less than 300 feet, a 7,200 feet per minute rate of climb, more than doubling the Skyraider's performance, and a top speed 500 miles per hour. Turboprop systems, however, were far more complex than pure jets, and their development, in fact, lagged far behind. The Sky Shark program was plagued from the outset by turbine and gearbox failures and a host of other engine-related problems which delayed testing and caused some serious accidents. As far as Heinemann was concerned, he was through with all manner of props. And indeed, even before the Sky Shark had commenced its flight trials, another, far more exotic Heinemann prototype was undergoing final assembly. It had been conceived in response to a 1947 Navy requirement for an interceptor capable of climbing from a standing start of 40,000 feet in 5 minutes. And it reflected just how far the turbojet and Heinemann had come in the 2 short years since the design of the F3D. Turbojet technology had matured at a dramatic pace in terms of engine weight, thrust, and fuel efficiency. And Heinemann and his design staff were now able to capitalize on this, making use of all the latest aerodynamic theory and all of the work done on the Sky Streak and Sky Rocket to create a truly revolutionary design. Intrigued by captured German research into the high-performance advantages of tailless, delta-wing platforms, Heinemann and his team refined the concept into a modified delta and came up with a rakish XF4D Skyray. First blown at Edwards Air Force Base in January of 1951, it offered the Navy a performer which at last began to fulfill some of the promise of the turbojet revolution. Naval aviators had wanted a high-speed interceptor, and that's what Ed Heinemann gave them. In October 1953, Lieutenant Commander Jim Burton went up in one of the prototypes and, flying on the deck, punched it into afterburner as he made 4 runs over a course at the Salton Sea in the Southern California desert. This speed for the 4 passes averaged out to over 752 miles per hour, and the Skyray thereby became the first carrier-borne aircraft ever to hold the world absolute speed record. Equally impressive, less than 2 weeks later, veteran Douglas test pilot Bob Rahn flew the same aircraft on the deck over a 100-kilometer closed course at Edwards Air Force Base and claimed yet another world's record as he banked around the course at an average speed of 728 miles per hour. Affectionately known as the Ford by the pilots who flew it, the F4D was the first Navy fighter capable of Mach 1 in level flight, and as an interceptor, it far exceeded the Navy's original 5 minutes to 40,000 feet requirement, as it established 5 world time-to-climb records, including a climb to 40,000 feet in less than 2 minutes. The design of this airplane was a remarkable achievement, which brought Heinemann a well-earned, long-overdue Collier Trophy in 1954. For many, this would have represented the pinnacle of a career, but not for Ed Heinemann. It was the largest and heaviest aircraft ever designed for routine carrier operations. Its genesis dated back to 1947, when the Navy issued specs for a long-range strategic bomber to be based on a projected new class of super carriers and capable of delivering the bulky 10,000-pound nuclear devices then in the inventory. The Navy had stipulated a maximum gross weight, including the weapon, of no more than 100,000 pounds. Ed Heinemann, however, didn't believe the supercarriers would ever be built, and thus, if the strategic bomber went into service, it'd have to operate from the much smaller, existing Midway-class carriers, which could never accommodate a 100,000-pound airplane. Thus, while industry and Navy experts continued to insist that the 100,000-pound figure was probably close to the absolute minimum for the mission, Heinemann set about to design a much smaller airplane, and when, after preliminary studies, he said he could get the job done within a gross weight 68,000 pounds, there were scoffers aplenty, and even the Navy was incredulous. His biggest problems stemmed from the heft of the 10,000-pound weapon, which required a cavernous bomb bay and had to be accessible from the cockpit so that one of the crew could arm it. Indeed, the whole logic of the design evolved from this consideration. Dictated, for example, the large, swept-back, shoulder-mounted wing, which in turn necessitated a narrow-track undercarriage retracting into the fuselage. As development proceeded, Heinemann stubbornly waged a constant battle against weight. Ed Heinemann, always weight-conscious, strove even harder to keep the aircraft weight well below the 100,000-pound limit, as he was convinced that construction of the supercarrier would be canceled as a result of the power struggle between the USAF and USN. Although doubting that Douglas could build an aircraft 2/3 the weight of its rival, the Navy gave Curtiss and Douglas a 3-month preliminary design contract to enable them to refine their proposals. Soon it became evident that indeed Ed Heinemann and his team would be able to realize their promise, and on 31st March 1949, Douglas was awarded a contract for 2 XA-3D-1s and a static test airframe. Named the Sky Warrior, the airplane exceeded all expectations when it went to the fleet, establishing a host of transoceanic and transcontinental speed records. The A3D excelled in its nuclear deterrent role and ultimately operated off carriers at gross weights of up to 84,000 pounds. Moreover, like so many Heinemann airplanes, it proved remarkably adaptable to a wide range of additional missions. Thus, in Vietnam, Sky Warriors would figure prominently in in such diverse roles as photo reconnaissance, mine laying, electronic countermeasures, and aerial refueling. Throughout its service, the Sky Warrior was the heaviest operational aircraft to operate from an aircraft carrier, which contributed to its nickname of Whale. German work on delta wing planforms, directed by Dr. Alexander Lippisch, led to a U.S. Navy proposal in 1947 for a short-range carrier-based interceptor fighter. Project studies were initiated by the Douglas design team, led by Ed Heinemann, with the object of producing a fighter optimized for a high rate of climb and capable of intercepting enemy aircraft. Heinemann initiated a study and found that for every pound of equipment or structure added to an airplane's original design, it had to grow an additional 10 pounds in order to maintain its original performance, speed, and range. The principal cause of this growth factor was, in his words, tack hammer engineering. Tacking on unnecessary additional systems, structure, and gadgetry, which, he explained, could be avoided with a little forethought. The cure, he said, was more diligent engineering, painstaking analysis of every single structural and system component in order to refine and simplify them to the maximum degree of efficiency. When the Navy asked if he could actually apply this philosophy to the design of a new jet attack bomber in 1952, he jumped at the chance. The spec called for a top speed of 580 miles per hour, an unrefueled combat radius of 400 miles, a 2,000-pound weapon load, and a max gross weight of less than 30,000 pounds. Confident he could exceed all of the performance goals while reducing the gross weight by more than half, he finalized his concept, and working with longtime El Segundo engineer and artist R.G. Smith, started roughing out a configuration design. And after considering a variety of shapes, structures, and entire configurations, the distinctive lines of the A4D Skyhawk emerged from their efforts. While the configuration underwent extensive refinement, Heinemann laid down the law to every member of his design team. Eliminate the unessential and cut the weight of each component to the minimum without jeopardizing its integrity. Such an approach resulted in a single wing box structure, for example, which was only 27 feet in span, thus wouldn't require the weight and complexity of a folding mechanism, and which would serve as a single, leak-proof integral fuel tank. By challenging every pound in the airplane, he proved that careful attention to detail spawned remarkable ingenuity. The short-span delta wing did not require the complexity of wingtip folding, saving an estimated 200 pounds. Its spars were machined from a single forging that spanned across both wingtips. The leading edge slats were designed to drop automatically at the appropriate speed by gravity and air pressure, saving weight and space by omitting actuation motors and switches. Similarly, the main undercarriage did not penetrate the main wing spar, designed so that when retracted only the wheel itself was inside the wing, and the undercarriage struts were housed in a fairing below the wing. Thus, the wing structure was lighter with the same overall strength. The Skyhawk proved to be a relatively common United States Navy aircraft export. Due to its small size, it could be operated from older, smaller World War II-era aircraft carriers still used by smaller navies during the 1960s. These older ships were often unable to accommodate newer Navy fighters such as the F4 Phantom II and F8 Crusader, which were faster and more capable than the A4, but significantly larger and heavier. The aircraft's 5 hardpoints support a variety of missiles, bombs, and other munitions. It was capable of carrying a bomb load equivalent to that of a World War II-era Boeing B-17 bomber, and could deliver nuclear weapons using a low-altitude bombing system and a loft delivery technique. The Douglas A4 Skyhawk played a significant role in both South and North Vietnam during the Vietnam War, serving primarily with the United States Navy, Marine Corps, and the South Vietnamese Air Force. In South Vietnam, the A4 was heavily involved in close air support for ground troops, counterinsurgency operations, and interdiction missions against Viet Cong supply lines. Operating from aircraft carriers and land bases, the Skyhawk provided quick response air support to U.S. and South Vietnamese forces, often attacking enemy positions, bunkers, and supply routes. The A4 was a key U.S. Navy strike aircraft against North Vietnamese targets throughout the war. It was frequently used in Operation Rolling Thunder, 1965 to 1968, where it bombed strategic targets, including bridges, supply depots, airfields, and transportation routes. The Skyhawk's high-speed, low-altitude attack profile made it a preferred platform for delivering precision strikes, but it also made the aircraft vulnerable to North Vietnamese air defenses. The Douglas A4 Skyhawk proved to be one of the most versatile and enduring attack aircraft of its time. From the jungles of Vietnam, where it provided close air support and struck strategic targets in the north, to the decks of U.S. Navy aircraft carriers, the Skyhawk demonstrated its rugged reliability and combat effectiveness. Though it faced increasing threats from enemy defenses, the A4 remained a critical asset throughout the conflict, shaping aerial warfare tactics for years to come. Beyond the battlefield, the Skyhawk found a lasting legacy in training and precision flying. Even after its combat service ended, it remained a vital part of military aviation, with some nations keeping it in operation for decades. Perhaps one of its most iconic roles came with the U.S. Navy Blue Angels, who flew the A4 from 1974 to 1986. In their hands, the Skyhawk became a symbol of speed, agility, and precision, inspiring countless aviation enthusiasts and demonstrating the aircraft's lasting impact. Though retired from frontline service, the A4 Skyhawk will always be remembered as a combat-proven, pilot-loved aircraft, one that left its mark in history both in war and in the skies of airshows around the world.